Warm greetings to all. Today I am here to present our work XAlign, Cross-lingual fact-to-text alignment and generation for low-resource languages. This work has been done in collaboration with Tushar Abhishek, Shiv Prasad, me Bhavijit, Anubhav Sharma, Professor Manish Gupta and Professor Vasudev Verma at Information Retrieval and Extraction Lab at IIIT Hyderabad. So the agenda of this presentation is as follows. Our work is primarily driven by the motivation of bridging the content gap that exists between English and other low resource languages. So basically the ultimate objective is to generate descriptive text in low resource languages using English triples which are present in abundance. However, such a model would need aligned data, and hence we contribute XAlign. XAlign is a cross-lingual fact-to-text dataset with close to 500,000 pairs. It spans across 8 languages, and out of these, close to 5,400 pairs, fact-to-text pairs have been annotated manually. As you can see, this is an example from our dataset. On the left, there is a set of English facts which have been aligned with various with sentences from various languages on the right. English facts about an entity Elon Musk are aligned with the following sentences that come from different Indian languages. Next, we talk about related work. Most of the existing work around data to text generation or entity linking has primarily focused only on English or a couple of other European languages. As you can see, there are existing datasets which talk about data to text generation like Wikibio, E2E, WebNLG, etc. However, very few of these offer a cross-lingual setting. Hence, our dataset XAlign is not just cross-lingual, it spans across 8 different languages including English. Along with this, existing fact-to-text methods include template-based methods like text-for-text generation, seek-to-seek attention networks, hierarchical attention networks, or pre-trained transformers. We have used some of these existing methods as baselines for our XAlign dataset in order to perform text generation in low-resource languages. That we'll discuss later. Next, we'll talk about the procedure and pipeline of data collection and pre-processing. So we start by gathering sentences in order to build our dataset. So for each of the 8 languages, we extract the text from the May 2021 Wikipedia XML dump, and we split the extracted text into sentences using Indic NLP. Furthermore, we filter out certain sentences in order to keep only meaningful and factual data by pruning out sentences from other languages apart from the target language, sentences which have less than 5 words or have greater than 100 words, and sentences which contain no factual information. In order to establish a filter for factual information, we basically use sentences which have at least one verb or one noun present inside them. Second, we start by gathering facts which would then be aligned with the previously gathered sentences. For these facts, we extract English facts from the December 2020 Wikidata dump. We retain useful factual information for the person entities, or basically for every entity that we find in our dataset from different languages. And finally, we end up extracting around 0.91 million facts extracted for 85,000 entities across all. Now coming over to our methodology and the pipeline of the alignment model, we'll talk about the fact-to-text alignment. The fact-to-text alignment was done in 2 different stages. The first stage was candidate generation. Here, instead of simply finding out the perfectly aligned facts for every sentence in a single go, we first try to filter out certain candidate facts which have a possibility of aligning with that particular sentence. This particular stage is aimed at providing a high recall, where we choose the top 10 facts that have a possibility of aligning with the given sentence. Hence, the aim is to not miss out on any fact which actually aligns with the sentence, while allowing the possibility of having extra facts which may or may not later on align with that sentence. Thus, we generate fact sentence pair candidates based on automated translation and syntactic and semantic match. The second stage, which is the candidate selection stage, provides a high precision. Here we actually filter out only those facts for every sentence that actually align with that sentence and contain the information that is present in the sentence. So the system architecture is shown here. We start by extracting descriptive sentences belonging to different languages from their corresponding Wikipedia. Then English facts are extracted from Wikidata. These sentences and facts act as input to our stage 1 aligner. The output of stage 1 aligner, which is basically the top 10 facts for every given sentence, act as input to the stage 2 aligner. After this, we finally obtain our XAlign dataset. This dataset is then used to fine-tune existing pre-trained multilingual models for the task of cross-lingual fact-to-text generation. Once we have a fine-tuned model, it is used to generate low-resource natural language sentences using our test dataset, which is basically a set of English facts. Now we'll talk in detail about the stage 1 of our alignment system, which is the candidate generation part. So for candidate generation, we compute a similarity score that captures syntactic as well as semantic similarity between a fact and a sentence. So for every fact-sentence pair, we assign a similarity score. The syntactic similarity is calculated by using features such as TF-IDF by translating either the fact, which is originally in English, to native language, or the sentence to English. For semantic similarity, we take cosine similarity between the mural representations of the fact and the mural representations of the sentence. Our stage 2, which is the final candidate selection for our cross-lingual alignment, fact-to-text alignment. For candidate selection, as already mentioned, the goal is to retain only those facts which strongly align with the given sentence. For this, we consider two approaches. The first approach is distant supervision from another English-only fact-to-text task. For this, we train a binary classifier on the Kelm dataset. This classifier is trained with the task of predicting whether the fact is associated with the given sentence or not. The second approach that we used is transfer learning from the NLI task. The NLI task is aimed at predicting whether a particular pair of sentences entail, contradict, or are neutral to each other. And our task is very similar to the NLI task. Thus, we experimented with various models like XLMR, MT5, Mural, etc. This table shows the F1 scores for various alignment methods that we tried. As you can see, the transfer learning approach when used along with the MT5 model performed the best and gave an F1 score of 83.7. Next, we talk about the manual annotation and our ground truth data. This table provides the statistics for our XAlign dataset. The MT5 stage 2 transfer learning aligner was run on the output from stage 1 and it gives the train and validation part of our XAlign dataset. For the test set, manual annotations were performed on approximately 5400 samples from different languages. This graph shows the fact distribution across different languages. As you can see, for most languages, more than 30% of their dataset contains just one fact per sentence, whereas close to 20 or 25% of their dataset contains two facts, and so on. Next, we finally talk about the cross-lingual fact-to-text generation. This table shows the results that we received from various text generation baselines that we tried. We tried a simple baseline where we compared just the fact translated in the given language. Next, we tried a simple transformer model on the given fact. Later on, we tried a graph attention network along with transformer, and finally the best performing baseline that we were able to achieve was an MT5 model. Blue performance, as it can be seen, is good for languages like English, Hindi and Bengali, whereas for other languages further work is needed. This table shows examples from the test dataset. The left column shows the input, which was basically English facts which were given to the MT5 model fine-tuned on our XAlign dataset. The middle column contains the reference text, which is the ground truth, and the rightmost column contains the text generated by the fine-tuned MT5 model. As you can see, the generated text is pretty similar to the actual ground truth reference text, and the model can actually be used for generating Wikipedia level sentences. Finally, the conclusion. So, through our paper, we proposed a novel cross-lingual fact-to-text problem. We contributed a new XAlign dataset for 8 different languages. We proposed 2 effective fact-to-text alignment methods that work in a cross-lingual setting. And we reported blue score results on strong baselines fine-tuned on our XAlign dataset. Following are the references and the papers that we cited. Thanks a lot.